Continuous distributions. Consider the graph of a function f of x displayed on this page. Suppose I drop a random point under that graph. Between that graph and the x-axis, the point here is labeled with an asterisk. I'm assuming here a certain kind of uniformity. That point is just as likely to be in any region of this graph of a comparable area. And I've recorded the x-coordinate of that point, labeled x along the x-axis, capital X. Then capital X is obviously some random variable. Let's assume, of course, that the function f of x is non-negative everywhere, and for convenience, assume that I've rescaled the y-axis in such a way that the total area under the graph of f of x is 1. In other words, I'm assuming that the integral from minus infinity up to infinity of f of x dx, that integral is 1. Note, of course, that by rescaling the y-axis, I don't alter the values of x. Suppose x is generated in this fashion. Here are some properties of that random variable x. What's the probability, for example, that x falls in the interval between a and b? This probability only depends on the area of the relevant region under the graph. In this case, the area of the slice between the points a and b under the graph of f of x. So the probability x is between a and b is the integral from a up to b of f of x, or the area of the region under the graph of f between a and b. What if we were to include the endpoints a and b? What's the probability x is greater than or equal to a and less than or equal to b? The difference between questions 1 and 2 is that in question 2 we've included the region immediately above the point a and immediately above the point b, that region being of area 0. It makes no difference, therefore, to the probability or to the integral. The probability x is greater than or equal to a and less than or equal to b continues to be the integral from a to b of f of x dx, identical to the answer to part 1 of this question. This is a first significant difference between continuous distributions and discrete. In the case of discrete distributions, it makes a difference whether we include boundary points or not. But for continuous, the probability of such points is 0. It makes no difference. Indeed, if we were to look at the probability x equals a, by a similar rule as before, we should integrate f of x from a to a dx, or use the area above the point a, which one could determine by multiplying together the width of the base, which is 0, times the height of the function at that point, f of a. Either way we calculate it, we end up with 0. For every point for a continuous distribution, for every point a, the probability that x equals a is 0. This is a remarkable and almost paradoxical fact, that for a continuous distribution, every single point has probability 0, and yet some point must occur. And of course, this paradox is partially resolved if you remember that the probability x equals a is the probability that's exactly a, not approximately a or a to 100 digits, decimals, but exactly a. There are an uncountable number of points a, and so each one can have probability 0, but when we add over an uncountable number by integrating, we end up with a positive value when we compute the probability of an interval. The cumulative distribution function. The cumulative distribution function is the probability up to a point b, including the point b. What's the probability x is between minus infinity and b? It's the integral from minus infinity up to b of f of x dx. So if we're interested in the cumulative distribution function of a continuous random variable capital X, then we should integrate f of z from minus infinity up to x. Indeed, this can be viewed as the definition of a cumulative distribution function for a continuous random variable. How are little f and big F related? What's the relationship between the cumulative distribution function and the so-called probability density function, little f of x? If I differentiate f of x with the f of x we obtained in part 2 of this question, and use the fundamental theorem of calculus, which says that the derivative of an integral up to x is the function itself, the integrand, we discover that f primed of x is equal to little f of x. The derivative of the cumulative distribution function is the probability density function, little f of x. In fact, this is embedded in the definition, our definition of continuous random variables and continuous distributions. we'll say that a random variable x is continuous if there is a function, little f of x, called the probability density function. We'll shorten that to PDF from time to time. So a function, little f of x, such that for any value a less than b, the probability that x is bigger than a and less than b can be obtained as the integral from a to b f of x dx, or as the area under the graph of f between the points a and b. And as we've seen, the probability density function, little f of x, is the derivative of the cumulative distribution function, capital F of x. Rounding a continuous random variable. You might well be wondering whether continuous random variables and continuous distributions exist, in fact. Because when you record a value, such as a weight or a height, typically you round that number off to the nearest inch or gram or kilogram or millimeter. And you end up, therefore, with a discrete random variable. What I want to look at now is the relationship between the rounded random variable and the original continuous random variable. We're calling it capital X. So suppose I have a continuous random variable, capital X, which has cumulative distribution function, capital F of x. And suppose I don't observe x itself, but I observe the value of x rounded to the nearest delta over 2 units. And we'll call that y. And we'll assume throughout that delta is small. For example, we're rounding it to the nearest inch or the nearest millimeter. It's the probability that the rounded value, y, takes the value little y. Y was obtained from x by rounding. Indeed, any value of x in the interval from y minus delta over 2 up to y plus delta over 2 gets rounded off to the same value, little y. So the probability we observe that value of little y is the probability that x falls in this interval between y minus delta over 2 and y plus delta over 2. This interval is labeled in the graph above. And of course that probability can be determined from the cumulative distribution function, capital F of y plus delta over 2 minus capital F of y minus delta over 2. Suppose the probability density function, little f of x, is continuous. Then the area of this slice in the graph above, the slice that's colored yellow, is approximately the area of an approximating rectangle, whose base is of width delta and whose height is little f of y. This is to say that the probability that capital Y takes the value little y is approximately little f of y times the width of the interval delta. So what's the meaning of a probability density function, little f of y? If we were to slide that interval from side to side, you'll notice that this probability will go up. The interval width will stay the same, but it'll go up as f of y increases and down as f of y decreases. Indeed, f of y represents the density of points near the value little y. It does not represent the exact probability of a given value for a continuous distribution.